stack to build one more stage amplifier. Yeah, before we do the next hand calculation. Okay, so in hand calculation, we normally have to buy the circuit correctly to give all the transistor have the correct operating point. For example, the current, the overdrive voltage. So which overdrive voltage is equal to the VGS minus VDS, right? We have already studied this in our course. And more importantly, the transconductance, because this will determine the gain directly, right? And the output resistance. The GN multiplied by RO is just simply our near DC gain of this amplifier, right? So the Heron analysis, which means that the output, when the output vary, so what is the linear operating region of this circuit? If the output vary too large, is it possible that circuit enters some other region that that transistor is no longer operate in the saturation, right? So this is a Heron analysis because we have to amplify the signal. Yeah. Okay, so this is actually the first order estimation, which means that we have neglected the other effect of transistor. Yeah. For this kind of circuit, we actually have to think other possible event like the breakdown, right? The breakdown or the linearity, and also the body effect, right? Body effect. The body effect will change the will change the threshold of this voltage we have to consider. But the hand calculation do not care about too detail of this. We just wish to know what's the limit of this circuit, and if this limit or if the spec already reached the limit of this kind of circuit, this circuit is not sufficient good to for us. So we have to think about other way, like the photocast code, right? Or other topology, right? So the simulation evidence will tell us what we should get and what we can observe from the EDA tools, like the transfer function, right? Transfer function, sometimes we will study. So what is the ability of one transistor? Normally, we refer to the response, right? The current voltage relation, right? And then when we build this circuit, we will think about the response, the high frequency response of this circuit. So what is the gain and the phase of this circuit? So why we have to study this? Yeah, because first we have to directly observe what is the near this gain of the amplifier. We still have to evaluate. So what is the bandwidth of this circuit? So what is the limit of this circuit when the gain drop to zero? At this point, we still have to observe the phase of this circuit. Why is that? Because we have to see the phase margin of this circuit. We must make sure this circuit, once it has been optimized, we must make sure this circuit cannot go into the oscillation region, which is an unstable region, right? In analog design, the amplifier cannot be an oscillator. Yeah. Okay, so we can also observe other waveform like the transient. Transient is a very direct way to help us to observe the input-output waveform, right? So we have a very small input signal. For example, the millivolt or microvolts input very small, right? But we have a large swing output because of the amplification. So from the transient, we can observe directly how is the waveform related to the input. So what is the actual amplification factor of this circuit? Actually, the transient simulation is quite useful when we design amplifier. Maybe the lecturer in the university do not tell you this truth. Why? Yeah, because sometimes if you worry about for example, the phase margin of this transistor, you can even enlarge the gain a little bit. After that, you observe the transient without giving an input to this amplifier. If under this circumstance, if you can still observe output at this amplifier, this amplifier may have gone into the unstable region. Yeah. Because the circuit become a self-start circuit, which means that without any input, you have a large output. So this is actually means the circuit already enter the unstable region. So the transient simulation is somewhat useful when we design amplifier to make sure the amplifier is safe, right? It's safe. Okay, so next one is the layout snapshot. Okay, the layout here is we have discussed layout before. So the layout we have to study a lot. For example, the common century matching for designing the differential amplifier to keep the matching between the differential core. So why is that important? Because a little bit mismatch would result in the DC offset of the AD output. So this is harmful, right? Also symmetric component pairing. Yeah, so how you can how you place the two transistors, how to connect them, how to make sure the symmetry of the interconnection, right? So clean routing, short connection, and also shooting of a sensitive node. So why is that important? Yeah, because in the SoC silicon SoC, right? We have multiple circuit block, for example, the microprocessor and also power amplifier. So these circuit are rather noisy, right? For example, the microprocessor will generate a lot of the sideband. I mean the harmonic of the beating signal. So these harmonic are actually large signal that can transmit inside the silicon chip, for example, through the interconnection, power line, and also the substrate, right? So if we do not have sufficient shielding, this harmonic will just go inside your circuit here. Yeah, just go inside the circuit here. Because this circuit is a operating amplifier, so the input here actually receive lots of harmonic from other block. So the circuit itself cannot distinguish useful signal or harmful signal. So it amplifies all the signal it can receive. So that's why we have to have sufficient shielding of the for example, the power line or the substrate shielding. Yeah, this is more specific when we have the course. Yeah, later. Yeah. Also, the next one, verification report. So this is for the layout engineer, yeah, to uh to export the verification and negotiate with the design engineer is for the DRC clean and LVS clean, and also PAX here means the post layout simulation. Yeah, if the we have to check if the post layout simulation fit entirely or similarly with the pre-simulation, and more importantly, after we extract the parasitic, we can still fulfill the specification here. And what is the margin between the specification and the post-layout simulation? Yeah. Okay, so we have done lots of talking for this slide. So next we discuss overview and cost objective. Okay, so analog. So in the real world signal, the signal is quite small, right? For the sun here, the signal is coarse and also small, and temperature variation can vary the response of the circuit. So other signal in the nature, for example, the light and also other effects can be amplified or can be sensed by our analog circuit. So for example, the biomedical signal, this is very small one, yeah, very small signal. So how can we amplify this signal? Yeah, a good news for us is that the biomedical circuit is a low frequency signal. So we actually sometimes we don't have to worry about too much of the circuit bandwidth. What we should worry about is the under such a small signal, how can we design a very low power signal that can tackle with this signal? Yeah, so this lead to a extreme low power design of the circuit. Yeah. So for RF and wireless signal, okay, so this signal is a high frequency signal. Yeah. For 5G and 6G signal is a millimeter wave signal. So it's already beyond or approach the cutoff frequency of one transistor. So actually to deal with this circuit, we have designed multiple stage of the amplifier. So the circuit is already very large and also consume lots of power. So commercial product, when you design a commercial product, you have to think about when you're competing with other company, right? How can you design a amplifier that meet the specification but still keep the power consumption as low as possible, and also make sure the noise level is not high enough to damage the bit error rate of the whole system. Okay, most device is basically like I think it's a semiconductor physics we have discussed about. Yeah. So next, the analog building block, we have to study something like comparator, which is a small signal device actually. Comparator is no longer a small signal. Sometimes it refer to a large signal devices because the input signal vary by a significant, yeah, from one small signal to a very high signal. So we will examine how the output respond to the input, right? And then a current source, yeah, we have to use a current source, for example, in the high precision reference. And how can we mirror such a current source to other branch of our circuit? So what is the percentage of the accuracy? I mean, what is the accuracy when you're mirroring this current? So if the currency is impaired, so how can we improve the accuracy, or how can we compensate for the loss of the during our mirror, right? The next one is the bias and reference. So this will study this topic when we study the band gap reference. Okay, next one is the filter. Yeah, filter means sometimes we have to filter unwanted harmonic of the circuit. For example, in the harmonic rich circuit, like in the digital combined with analog circuit, sometimes we have to use the filter to filter out some digital circuit before the signal can enter into the analog circuit. Otherwise, the harmonic will be amplified by the operating amplifier you have designed and saturate the output. So what's the problem of such saturation? It makes that because your input signal is rather weak, and the harmonic already saturate your circuit, so you cannot get what you want at the output. The output is already saturated. So that's why sometimes we have to filter out unwanted harmonic. Yeah. Filter is commonly observed in many analog circuit like PLL, right? The clock. Yeah, the filter actually create a zero pole distribution to make sure the circuit to be stabilized. Yeah. Okay, the next one is oscillator. Yeah, oscillator is a self-stop circuit. Self-stop means that without any input signal, the circuit can operate itself. Yeah, this is for the oscillator. Yeah, we will study this almost at the end of this class now. Okay, so the signal chain. Okay, so first we have the sensor, right? We have a sensor. Sensor means that we have sense the signal. So what signal we have to sense? For example, the light, right? The lights. Also, the temperature is also signal that we can sense. And biomedical, not biological, biomedical circuit, and also the radio frequency wireless signal we can sense. Yeah. After sensing, sometimes sensor also means the converter circuit. So why we say that? Because the input signal is not electronic signal, is other physical signal. For example, the light. The light is not electronic signal. So the sensor here have to convert the light into electronic signal that can be adjusted by the subsequent device. Here, the sensor, if for light, then the sensor converts the light signal into the current. So the current will be transconducted by an amplifier here, which is a TIA, the transconductor amplifier, right? By a TIA that can the output of the sensor, which is current, is sometimes is in proportional of the strength of the light signal, right? So the amplifier can then boost the voltage swing for the received light. Yeah, sometimes the sensor is a passive device, so it introduce loss when it do the conversion, right? So the amplifier here is necessary at the first stage of the signal trend because it has to increase the signal to noise ratio at the beginning. So I think most of you understand. So why it's important because signal to noise ratio directly determine the bit error rate of the signal trend. So the first stage must be an amplifier or a TIA, right? The trans impedance amplifier. Yeah, trans impedance amplifier will convert the current into the voltage, and then the voltage can be processed by an analog to digital converter. Yeah, so the ADC here convert the input signal, so which is large enough to a digital code here, right? So this digital code can feed to the DSP logic for subsequent processing. After that, after the processing, the digital code will directly drive the DAC. So this DAC will feed back to the ADC to tune the parameter of this ADC. So why is that useful? Because the ADC sometimes do not know. So what is the required amplitude, the input amplitude, the requirement for the input amplitude. So after it output the digital code to DSP, the DSP will understand. So what is the current input? So if you tune the ADC by a DAC here to get the ADC operate in the optimal region, right? Okay, so this is for the signal trend. So system application is more likely to be an embedding system. Yeah, it's a systematic level issue. Yeah, it's more complex than before, but I think this is somewhat open for the undergraduate student. Okay. So next we talk about our course objective and the teaching method. Okay, so we can equip you with the principal institute children practical skill need to design high performance analog integrated circuit. So at the beginning, we have to gain sufficient knowledge to understand the core principle. Yeah, understand the fundamental of analog circuit behavior, especially the input-output response and device physics. So what is the limit of the transistor? So what is the first and the second effect, and how it can affect a real design? And then we can ignore this effect. Yeah, so we have to understand device physics and also the system level thinking. Yeah, system level thinking sometimes refer to when you have a big project. Yeah, the big project normally composed of many circuit block like amplifier. So here, so from this perspective, so what is the requirement for one single amplifier? Yeah, because you design this one. Yeah, when you design this one, you have to understand. So what is the limit for other circuit block? So how is the performance you design here can affect or degrade other block? So how much margin do you have when you design this circuit? Yeah, so sometimes you have to sacrifice something, yeah, to meet the specification. So what is the margin you can get when you design this? Yeah. And then analyze the design. I think this is more important when we conduct the lecture. Yeah. So analyze and design. Sometimes here we have I think we have a hand calculation. Yeah, we have a hand calculation. So first step we have to know how to do a hand calculation, analyze design and simulate building block. Yeah, analyze means that we have a spec and then we'll think about some topology to meet the spec. So let us do some hand calculation before we simulating this circuit. And before we conduct a simulation, we must understand what is the limit of this circuit and how their parameters trade off each other, compromise each other, right? And also make informed trade-off, which means that uh, the parameter among the within the circuit are actually fight each other. For example, the gain, you have a higher gain, but you have to sacrifice something like the area and the power consumption, or even the bandwidth. Yeah, if you keep the power consumption the same, you increase the gain, but you have to sacrifice the bandwidth. So actually, you face this trade-off. Yeah, noise, power, speed, and area to meet the specification. In this course, we normally think about noise, power, gain, speed, and at the end, maybe during your training later, you think about how to reduce the area to meet the specification. Yeah. Okay, so what can we get from our lecture? So we can explain, apply analog circuit fundamental and key metrics. We understand so the key metrics of the circuit. We know what is the important performance for this circuit. Okay, so design, analyze, amplify on common building block. Okay, so we'll study multiple configuration of the amplifier, and we still have to make comparison between among different block. So understand what what is the respect limit of each amplifier, and why other topology can solve this can reach beyond the limit of the current one, but other configuration also have its own issue. So we finally have a comparison table to summarize the performance metrics between different amplifier and building blocks. And we also do hand calculation to analyze, I mean to quantify the optimize the linearity, noise, and dynamic range. So this is I think this is a higher thinking. This is more difficult than a good hand calculation. So it's basically relies on the EDA tool to help us to understand. Yeah. Evaluate power, speed, and stability trade-off. Yeah, this must be supported by our EDA tool. And then we integrate block into complete system and verify performance. Yeah, once we have multiple design and each of them already meet their respective target, then we can try to complete this, to integrate this building block and evaluate their performance after they are integrated, and to see so what what performance degradation through the integration, and what is the root cause of this performance degradation. So back to then, we have to return to the phase one to maybe to tune each block so that after their integration, they can still meet the time requirement. So this is basically I think more challenging for the high frequency design. Okay, so what is the possible teaching approach? So the first we have to strengthen our basics, right? So we must understand the concept and build intuition through our through explanation, and sometimes we have to link the equation between different parameters. Okay, next we must have a real case study for our study. Yeah, we must have a real circuit block for us to analyze, to do the hand calculation, and also to evaluate their performance metric. Okay, and next, once we understand the circuit fundamental, so we can simulate this circuit by our EDA tool and observe if the result can fit our analytical result. So if we cannot observe a reasonable result in our simulation, so we have to think about our hand calculation is correct, or our simulation our simulation method is correct. So through this interactive study, we can gain both ability for our analysis and the transistor level simulation. And then this lab and mini project, I think, is at the end of this this lecture, this season. Yeah, at the end of this lecture, for each student, we will have an individual project. I think it's not a very difficult one. It's not very difficult one. I would just make it simpler for each of a student. It can be a uh, open loop operation amplifier, uh, or a current mirror, or a LDO, or even a temperature sensor. But all of them are not so difficult to design. Yeah, some design have already. I will show you the schematic, but you have to tune the transistor size to make it operate, to make it function correctly. At the end, you will tell me why you choose this size and why you think this size already leads to optimal performance you can get. So at the end, you have to not just done lots of simulation. Yeah, you at the end you tell me, so why this sizing is good enough. Yeah, so you have to explain the reason. Yeah. So later we will have a discussion and feedback. So by uh, by the end of this lecture, yeah, after you submit the report for your lab work, yeah. So the knowledge map. Okay, so knowledge map. First is the concept. Yeah, we must understand the basic concept for the each type of simple amplifier. Okay, so how the device and how the semiconductor device can affect the ability of your decision, right? So what is the limit? What is the device limit? And how this device limit affect the limit of your circuit? Yeah, for example, you cannot go very high the voltage level, yeah, because it will cause breakdown. And then the small signal analysis. This is a very basic fundamental for all of the student here, I think. Yeah. And the feedback and stability, this is more difficult than single stage amplifier, right? Because the feedbacks, I think most of you already know there are four types of feedback, right? Four types of feedback. For example, current voltage, and current. Yeah, the four types of feedback for the operation of amplifier. Sometimes the feedback comes from internal node, yeah, come from internal node. So what is commonly observed is the CDS, right? The drain to source, the capacitance, which is create an internal node to for the feedback. This will actually harms the stability of the amplifier. The feedback can also come from global feedback, right? Global feedback is actually somewhat uh uh I mean I mean, this global feedback is actually created by designer, right? Not by sometimes not by the circuit itself. It's created by the designer to fulfill some spec. For example, the sensitivity to the change of the for example, the input signal, right? To desensitize the design, right? So why is the stability is quite important here? Yeah, because the feedback sometimes will enhance the pole. I mean to enhance the pole of one of some internal node. So it can create uh, stability issue. Yeah. So we have to before we connect the before we can connect the feedback. So we must do a quick hand calculation to evaluate if we connect the feedback. So how the pole zero distribution will arrive such that the system can go into an instability region. So for this at this stage, you have to draw the border plot, right? The gain phase relation, and we must observe when the gain drop to zero. So what is the phase right now, and what is the phase margin of this scenario? Yeah, normally we prefer phase margin larger than 660 degree, but if we can go, if it is still small, for example, smaller than 30, so if the temperature or the environment effect comes, your circuit may eventually go into an unstable region. Yeah. Okay, next one is the linearity and the distortion. So linearity sometimes referred to a large signal input. Yeah, for small signal input, if your gain is reasonable, sometimes the circuit operate in the linear region, right? Because the transistor for the amplification stage, the transistor can operate well in the saturation region. Yeah, and other transistors also operate in their respective region. But if the input signal is large enough, sometimes you cannot control, right? You do not know what is the level of the input signal. But if the input signal is too large, some devices may enter into other region. Yeah. For example, because the input is time varying, at one moment the amplification stage operate in the saturation region, but in another time frame, some transistor enter into the trial region. So what is the problem of this issue? The problem is during this time frame, your circuit already have lower gain because some amplification stage not operate in the saturation region. So the output waveform will become distort. So this is the cause of the distortion, right? Distortion. Actually, if you have experience on the power amplifier design, you will understand because the input signal is large enough and the gain is too high. Sometimes the output saturate for some time interval, even a short time interval, but still vary with the input another time. Yeah. So what's the result of distortion? Actually, if from our signal and processing knowledge, this will generate a reach of harmonic to distort the subsequent circuit. So it's actually not a linear circuit anymore. It instead become a non-linear circuit because it generates harmonic of the input, right? So what is the boundary between the linear and non-linear? For linear circuit, the actually the output just mimic the input waveform. The only difference that the output boosts the input signal swing, right? The input is a sine wave, your output should be a pure sine wave. But for distorted circuit, which is a nonlinear circuit, if you generate the harmonic of your input sine wave, for example, the second harmonic, third or fourth or other higher harmonics. So what is the problem here? So the problem will desensitize the subsequent circuit. For example, for if the next stage is a mixer or other missing components, this higher harmonic will mix with the clock frequency and generate undesired harmonic and amplified by the subsequent devices. So because your circuit is nonlinear, the system will eventually amplify many unwanted harmonic signal and then deal with by the subsequent ADC. The ADC cannot understand. So what is your desired signal and what is the interference? So this will cause the bit error rate of the system or cause the system malfunction or degradation. Yeah. So linearity sometimes is also very helpful, very useful parameter. Yeah. I think many of students think the amplifier should have very high gain, right? The higher gain, we get a higher score in our final exam or at our final report. That is not really true. Yeah, there's no because we have to think about the linearity and also the distortion. Yeah. Okay, next one is noise and dynamic range. This is somewhat difficult topic. Yeah, noise is actually is just a fully random signal that also although it's a small signal, but it's a random signal that impede the uh, harm the amplifier. Yeah, we will go into the detail when we conduct the lecture. Yeah. So finally, what we can gain from our lecture. So the first one, we get a strong foundation of what we learn. Yeah, the fundamental of the circuit and how. So what is the input-output relationship? What is the limit? So what is important here? For example, small signal analysis, and how can we build a feedback? And what's the stability issue? And importantly, what is the linearity of your design? And design intuition. This is very helpful when you do the interview. Yeah, in the future. Yeah, because you know the when you do the interview, there are lots of uh participants. Yeah, so the expert actually just maybe just take 10 minutes or even 15 minutes with you. Yeah. So design intuition will just give if you have sufficient intuition, you can give the expert direct answer. Yeah. Uh be, before too much discussion, right? So you can actually you can save a lot of time during the interview, but still answer properly to the expert's question. Yeah. And the real world skill means that actually we will have a project. For example, the operational amplifier or even LDO or some voltage converter. Yeah, later we will have we can get a skill by designing a real world circuit. Yeah. And then a better engineer means we get sufficient experience if because we can study how to tune the circuit and why we can get optimized results by our from our tuning, right? And how can we draw the layout for each design? So what is the problem when we draw the layout? Yeah. Also, the next one is career advantage by studying this course, and we will understand what the industry need from our student, right? Why this course is important to you. So more importantly, I think we can mimic a real interview situation to for example I can become the expert and then your student here. So we can have something like interview here. So you understand how the expert will ask question. Yeah, and what's your way to answer quickly to each question. Yeah. Okay. Okay, I think I will skip this one because already discussed before. Okay, so next part two, we discuss cost relevant and prerequisite cost. Yeah. So cost relevance where this program fit. So analyze design actually connect basic circuit theory and semiconductor physics. Yeah, we have talked about, and also signal and system. So so many students in China ask why signal system is important for studying this course. They understand why semiconductor device important, why signal and system important. That is because sometimes we do not know what is the level of the input signal, right? As we have mentioned before, yeah, we cannot determine what is the input signal level. If the small signal is low enough, which means that it's actually for the amplifier, it's a real small signal. The amplifier will act as a linear device, a linear amplifier to amplify the input incoming signal. But if the input goes higher, I mean the voltage goes higher, the device, the amplifier here, yeah, as we have mentioned, will become a nonlinear device. Yeah, it will generate the harmonic at the output of the incoming signal. So that's why we have to study signal and system to evaluate the response of such a nonlinear device to estimate so what is the level of the harmonic at the output. Yeah, and then we have to evaluate where how this harmonic can harm the subsequent circuit. So we understand if this occur, I mean the large signal come. So if this occur, how can we design a subsequent filter or other device that can sufficiently filter out the unwanted signal? Yeah. We can also study how we can design a more linear operating amplifier by sacrificing the gain. Yeah, so this is an interactive design procedure actually. So this signal and system is also important when we start this course. Okay, EDA tools, yeah, for the simulation, layout, and real application. This is for a real project. Yeah. Circuit theory. So we started the base theory of the circuit device physics link. So we understand what's the limit of the device. Why we cannot go freely high the voltage because it causes breakdown and other issue, right? We understand some breakdown can be reverted, but some cannot be reverted. Why this is important? Because when we design some circuit like the voltage control oscillator, the output signal actually can vary from 0 voltage to a rather high voltage, which is already close to the supply voltage. So at this case, the transistor will experience off, saturation, and linear region. So if you experience all region of one single transistor, if the signal becomes high enough, for example, approach or even higher than the supply voltage, this transistor will face the breakdown issue. We must understand under this issue if the breakdown is revertible or non-revertible. Yeah, if this is non-revertible process, then the transistor may be broken permanently, and the circuit will become malfunction. Yeah. So, however, if the breakdown is revertible, so maybe it is safe for us, right? Is because it is revertible, so it's somewhat safe. But we must evaluate the lifetime of this device because it somewhat enter the breakdown region. Yeah. People will ask why the signal voltage can be higher than the supply voltage. Yeah. So we will study this when we conduct the course, right? Okay, next one, signal processing bridge. So bridge signal and system concept to analyze, shape real world signal. Yeah, we will have a real project and we will observe the input output response and also more likely to observe the harmonic generated by such a nonlinear device. Yeah, we can get lots of knowledge through this simulation and comparing with our hand calculation. Yeah, sometimes hand calculation cannot fully cover the nonlinear characteristic. Yeah, because this is too difficult for undergraduate student. But we can rely on the EDA tool to tell us so what is the cause of the nonlinearity. So and what is the level of such nonlinearity? Is it high enough or it can be ignored? So we can bridge signal processing, yeah, to our real case study. Yeah. EDA and verification practice also, I think, is really important. Yeah, because we must fully understand our circuit. Yeah, without the support from EDA, could we stop at the hand calculation? We do not know how the circuit will respond with different input level, right? Okay, system application, I think is more complex topic, so we may discuss later. Yeah. Okay, so what's the connection to core universal course? I think we have studied this before. Yeah, circuit analysis, analog electronic. This is a basic course in the first year. Semiconductor physics, quite important in the second year and third year. Signal and system. Yeah, as we have mentioned, this is useful when we discuss a distortion of the amplifier. And microelectronic, yeah, this is big word, big word in China. This is actually a department name. Microelectronic is the department name in China. Yeah, EDA tools mean simulation, IC layout. Yeah, we have to gain some layout experience before we go to the industry. Yeah, the expert during the interview will ask you something about the IC layout. For example, the symmetry, right? How to do the symmetry, how to prevent the long routing, and how can you block the each circuit block. So what is the problem if your layout after layout simulation is quite different from a post layout simulation? So this I think the expert will ask you several critical questions, yeah, during the interview. Yeah. Okay, so pre-request knowledge for this course. This is just some actually. I'm sorry, this is a repeat slides, but I will not go into detail anymore. Yeah, so this is Kirchhoff current law, Kirchhoff voltage law. I think all of you have studied before. Right? So this is basic circuit analyze approach in the first year study. And voltage, current, power. So what is the relation between them? Series, parallel, and voltage current division. Yeah, this is some quite fundamental knowledge in our first year student. And the second one is much more difficult for many students because this is related to the physics. Yeah, that is a very somewhat difficult one. Yeah, for the simple diode, we all know diode, right? Yeah, IV characteristic. So someone remember what is the relationship? Yeah, it's a exponential relationship, right? You have a small input. The diode is off after about 0.7 voltage. 0.7 volts, the diode start to conducting, right? Conducting current. But if you continue to increase the input level, the current will go much higher and quickly. Yeah. Versus the input. So this is actually exponential input. I think we still have to go back to recall. So how can we derive such a relationship, right? So forward reverse bias. So this is all important because if you affect, so the placement of our diode is for forward use or reverse use, right? So for forward use, so what is the specific circuit to protect this diode because the current is too much. So we have to put a series resistor to make sure it's safe, right? For reverse bias, why we show why you put this diode as a reverse bias? Sometimes we use as a tunable capacitor, right? Yeah. When we use as a tunable, I mean the variable capacitor. Yeah, normally we use a diode as the reverse bias. So how can we do that? How can we measure reverse bias? So we have to think about, yeah. So for the MOSFET transistor, it normally composed of three node, right? Gate, drain, and also source. Sometimes if we consider the second effect, we have to consider body, right? The body bias will vary the threshold voltage by the second effect, right? During the layout, the body is very important, right? Because it's quite sensitive to noise and the interference. So if we do not have sufficient block device, or if we do not have sufficient and I mean the isolation, so the harmonic or noise will go through the substrate and affect the body of one single transistor and vary its threshold voltage. So it's more likely to be a modulation, right? Okay, so if you have experience in university working on the measurement for your senior student, sometimes if you have something like a voltage control oscillator or some other large signal circuit, you will see in the spectral analyzer the harmonic of the signal. The harmonic, the place of the harmonic is quite different from your desired signal, and sometimes you do not understand how come of this signal. It's actually the bypass. I mean the bypass. I mean the propagation of the noise through the body, right? Through the body. So why through the body? Because the body is shared between among all transistors is a P plus region, right? P minus region, the substrate. So the signal can the harmonic can actually propagate along the silicon substrate to affect your transistor. And how it can affect it, create a varying signal at the body and tune your transistor threshold. By this way, it appears that in your spectral analyzer you observe a harmonic of the signal from other block. Yeah. So so uh so these body effects it cannot be ignored. Yeah. Most operating region. So this is very basic in our study in the third year. Yeah. For the cutoff, so the VGS smaller than the threshold voltage. So the transistor remain in the off because the inversion layer has not been built for this case, right? So how about we further increase the VGS, the gate source voltage, then the inversion layer is built. Yeah, it's built here. But it's still, because the voltage is still not large enough, the inversion layer is rather small, right? Rather small. So the the extra electron just come and say, wow, the hole in the channel. So under this case, the current is small. Yeah. But if we further increase the VGS and then ensure that the drain source voltage is higher than the VGS minus VTH, we can have a complete immersion layer here, right? Immersion layer here. So at this case, we can get a higher current, the higher level of current than the triode region. Yeah. So how about we further increase the VDS? So how about we further if we further increase the VDS, the current becomes saturated, right? The current becomes saturated. So how in this case, how can we further increase the current, but we have to increase the VGF of this transistor, right? So this is a fundamental of the device physics. Yeah. Okay, next one is signal system. Yeah, we have just talking about is mainly for discussing the amplifier in high frequency region. So we wish to understand uh, how the amplifier we have designed can respond to a high frequency input signal. And of course, without input signal, we have to ensure uh, ensure the op, the amplifier operate in the safe region. So we have to understand even if without input signal. So what is the gain and phase relationship of this amplifier to ensure it operate in the non-oscillation region, right? Okay. Okay. So I think we have discussed this before, right? So the skill we can get, so specification, so understanding the matrix between performance, what are the limits? How can we reach beyond the limits if we sacrifice something? And how can we analyze a simple circuit? And how can we simulate by our EDA tool? And so what is the waveform we can expect from the simulation tool? So, and how we can debug the circuit using the tool. Okay. So in the real case design, so at the end we will have a real case design for each student. So support. So how can this design support our study. So first we have to run the simulation to verify our circuit. The goal here is to observe the input-output waveform. If this waveform is reasonable enough, according to our analysis. So for example, yeah, but this is for measurement. But before measurement, we have to run simulation, right? So sometimes we can observe non-ideal output even at a simulator or in the measurement, and we have to identify why this how this difference come from. Yeah. So what is the during measurement? What is not what we can use to measure the signal? We can use a oscilloscope. Yeah, in many cases we can use the oscilloscope. Yeah, to observe the input-output waveform, and we can calculate the input to output amplification factor, and we can also use something like a spectral analyzer. Uh, Using spectral analyzer will give us the frequency and the amplitude of the output. Still through this way we can still get the output power of the amplifier. Yeah, so we can still evaluate the true power of the amplification, and we can also evaluate the harmonic frequency and amplitude of the harmonic through our spectral analyzer. Yeah, so this is for us to study during our measurement. And if we observe something that quite different from our simulation, for example, in most of the case, if the chip is malfunction, I mean the chip is not working. So normally the first step is to check the DC bias point of your chip is correct or not. For example, if your chip consume micro 10 mic I mean consume 10 microampere, yeah, from the DC supply. But during your measurement, you observe nothing in the screen. So you have to check if the current for your circuit is correct. If it is correct, close to 10 microamp, or go beyond or smaller than it, or significant larger than it. Okay, so in the first case, your measured current is somewhat smaller than your similar one. This is quite common because the PCB bonding and also the other interconnect loss have decreased the current flowing into your device. So under this case, you will somewhat have to tune a little bit higher voltage than the simulation result until your current fit closely with your to your simulation result, and then you observe again the screen if the result is already close. Other case, in the opposite case, which means that the current the measured current is even higher than a similar result of your current. So at this case, the result is more complicated. For example, if the circuit already operate in the oscillation region, yeah, so the circuit normally operate in a large signal region. It must drop a lot of current from the DC supply. Yeah, so you have to, during this case, sometimes you cannot observe the waveform from an oscilloscope. Why? Because your circuit may oscillate at a much higher frequency than the oscilloscope can detect. For example, some oscilloscope in your university can observe frequency lower than 100 megahertz. Yeah, because it's cheap, right? It's cheap for student for during for conducting daily measurement. However, you cannot use this oscilloscope to observe a real circuit because circuit may oscillate at a much higher frequency, for example, 1 gigahertz or even higher. Yeah. So for this case, you have to use the spectral analyzer to swap all the possible point of your of the output. If you observe the spectrum without providing the input, the circuit must enter the unstable region. Yeah. Please do not ignore this issue. Actually, this is somewhat common in lab. Yeah, even for a PhD student, this is very harmful to your circuit. So why this is happen? It happen because sometimes we ignore the analysis of the stability of circuit, or sometimes we have to make paper publish, right? We presume a higher gain of our circuit, so sometimes we lack the simulation on the stability issue. Sometimes when you observe your current is small, then the simulation result you wish to increase it. But after you increase it, the transistor may enter into the oscillation that have not been fully uh, understand during your analysis, right? So this means that it is a interactive process between the measurement and your simulation. During your measurement, you observe the output waveform, and then you go back to your simulation until the uh, until the bias point is just close to each other. Then after that, you measure other performance like noise, gain, and other important uh, parameter. But please make sure the DC bias point is close to your simulated one, and do not allow the device enter into the oscillation region. Yeah, once your device enter into oscillation, I think the chip is fail in a fashion, right? In another fashion. Yeah. That normally the chip fail without consuming any current is like dead tree, right? So that dead tree. But in another failed chip, it oscillate. Yeah, unless you really desire oscillation, oscillator, right? This is different. You can just change. You can consider changing your PhD direction from amplifier to the oscillation, maybe. You think this is fit. Ah, but I think this is a tragedy if you chip really enter into oscillation. Yeah, just be very cautious on this. Okay, the lab 3 amplifier gain bandwidth this interactive design process. Yeah, when we have higher gain, we normally sacrifice the bandwidth. This is for us to train our thinking on the trade-off. Yeah. Okay, noise linearity and dynamic range. This is higher. I think this is a harder topic. Yeah, this is more challenging for undergraduate student. But we still study this topic during our lecture. Yeah, we will derive some useful equation to estimate the noise linearity. Yeah, and the dynamic range. Okay, the final one is the layout. Yeah. Okay, part 3 introduction. And so we have I think we have discussed before. So why we still need the analog circuit is to sense and amplify some small signal from the environment, like temperature, sound, light signal. We have discussed about. So then after the amplification, we need to perform the conversion, right? Why we need a conversion? Because a digital processing chip can only understand digital, binary digital. So we have to have some we need to have some conversion circuit to convert the amplified signal to the digital format, right? So this time we need a analog to digital converter, right? So analog front end determines system quality. So why is that? Because, for example, the noise generated by the analog circuit, although the analog circuit can amplify the signal, right? Boosted its amplitude from a rather small signal to a large signal, but it also introduces noise to the whole system. Yeah, this noise will create some random perturbation with the signal. So the digital processor cannot distinguish from the original of the signal and the noise. So the noise is actually mixed with the input signal, even though they are although they are amplified by the same factor, right? So so the analog circuit must have low noise but still high gain to amplify the signal. Yeah. Another problem is the distortion we just talking about, right? So the distortion will actually confuse the following digital signal processor. Yeah, because this DSP cannot distinguish again from the desired signal and the harmonics. Yeah, if the harmonic power is comparable with the input signal, the DSP will calculate both signal, and we cannot get a solid or correct result at the end. Yeah. So here we must minimize the spur or harmonic generation in our analog IC. Okay, so a common practice is to design a high linear amplifier, but sometimes high linearity means that we have to sacrifice something like gain. So to think about this, we either rely on a redesign of our amplifier, or we have to design some specific filter to filter out the unwanted harmonic, right? Okay, so dynamic range, and this is referred to the noise level and signal to noise level of the device. And power efficiency, yeah, this is very important when we design a customized chip or the product, because the customer uh concern about the power efficiency more than sometimes the performance of the whole chip, right? Okay, the robustness is also important, which means that when the surrounding environment change, so how your chip can be resilient, or how your chip can respond to the environmental variation. In a ideal case, the chip change nothing, right? Change nothing with the environmental variation, but this is not possible. Yeah, because for example, the temperature change when we deliver the chip from, for example, from Russia to Malaysia, so the temperature will go through minus maybe 40 degree, right, to 20, right? So it's a big change of the temperature. So this significant change will make the chip operate differently. So the robustness ensure the chip work normally in regardless of such a environmental chip variation, right? Another case is the electronic magnetic influence from the outer world, from the outside world. I mean the space, right? I think many of you have heard that some AI chip have gone into the space, right? So this chip must witness a reach of electromagnetic interference from the outer space. Yeah, so this cannot be ignored anymore for this chip. So this chip must be sufficiently strong to filter out this interference, or it can deal with this interference internally in the chip itself. For example, by some cancellation algorithm, or if you have read some paper recently, they sometimes refer to the noise or interference cancellation circuit. Yeah, so this circuit is able to cancel the incoming interference itself, but still gain the ability to amplify the incoming signal. So it is smart, right? It is a smart circuit to distinguish the useful signal between from the interference signal. Yeah, so it amplify the useful signal but cancel out the interference. So this makes chip quite robustness. However, I think many of you this product still remain in laboratory. So why? Because this kind of circuit sacrifice many aspect of the performance. So it is still a research work. Yeah, remain in the lab, but it's quite it already has a very high potential to replace existing design, probably in the future. Yeah. So I think if you study this in your master or PhD study, or if you go into the industry, you will investigate how you can build a robustness to the chip, right? Okay. So analog IC power key, so application everywhere. So, for sensing, for example, sensing the temperature, pressure, and also some other physical signal. For example, light, or used for the biomedical or industrial sensor environmental monitoring. For example, monitoring the temperature variation or the light variation, right? So it's a highly sensitive analog design circuit. Yeah. And second, it used for communication. So right now we are moving toward the sixth generation communication, right? So 5G is I mean the fifth generation remains in the radio frequency region, which is already approximately 10 gigahertz or below for the RF transceiver. However, for the future usage, we have to move to the millimeter wave region, which means that the carrier frequency will easily go beyond the 60 gigahertz, right? Or even 100 gigahertz is quite high frequency. So our analog circuit must be able to amplify such high frequency signal and also have sufficient low noise to tolerance the noise during the transmission, right? Because the signal is transmit and propagate through the free space. The free space have lots of noise and interference summing into the useful signal. So in many cases, for example, for GPS signal, the interference strength is even higher than a useful signal. So your RF transceiver must be smart enough to identify what is the useful signal and what is the interference. You must distinguish between them and use our knowledge study here to amplify the useful signal and filter out unwanted signal. Yeah, we'll gain knowledge how to design circuit particularly for such use. Okay, there are many kinds of communication chips. For example, the Wi-Fi, yeah, and Bluetooth, and also GPS or GNSS, and also our data link, right? Data link is commonly observed in the data center, right? For the uh I mean for the very high speed communication between different server or computer center, right? So high speed wire link, I think some of you have already heard this, is a really high salary, a very well paid job right now. Yeah, but it's also rather difficult because the requirement for this job is rather high. I think undergraduate knowledge is actually not enough to fit this job. At least a PhD degree is more suitable. Yeah, for this high speed wire link or wireless. Yeah, because actually this area, yeah, combine many knowledge from uh, different aspects. So it's integration of many knowledge here. Yeah. Okay, power management. Okay, is a DC converter and LDOs. I think this is reasonable for undergraduate study. Yeah, battery charging and fuel gauging, power efficiency protection. Yeah, something like that. Yeah. Okay, so I think in the second years and I think it's an analog circuit design, not analog integrated circuit design. We had in during the first class, we already started this the signal chain, right? So we sense the signal from nature, for example, temperature, sound, light are our small RF signal. And the first stage we have to amplify, then we have to do the filtering, yeah, to prevent the interference uh, to impede the subsequent circuit. And then we here is a signal conditioning, but sometimes is maybe referred to some buffering because the impedance matching between the filtering and the next stage is like buffering, right? So the next stage is the protection, multiplexing. Multiplexing means that if you have multiple paths, right? Normally the signal chain have lots of paths, not just one path. You have multiple paths to choose what's the signal direction and flow to the in the signal chain. Yeah. So the next one is ADC, right? To transform your input linear continuous signal into discrete signal. Yeah, which means that the signal will go into the digital world by this ADC. And then the signal processing block will analyze the signal, yeah, and feedback. Sometimes we will give a feedback to the ADC to tune its performance. Okay, or it also output the digital world to drive the subsequent device, such as the monitor, and also power amplifier here, and also some other control, right? So this is the basic signal flow of our signal of our system. So in this course, we focus on the design of the amplification and also the buffering. So we'll do lots of analysis on how to design a amplifier. Yeah. And we also have some study on how we can do the filtering, but we still focus on design of the amplifier. Yeah. And later after you go to industry or go to the master PhD study, you will study other complex block like the ADC, right? And also other useful block like DCT converter or LDO. LDO is very important here because we will provide a supply to all of the stage here. Yeah. As we know, we cannot directly connect this amplifier to the 220 volt voltage, right? We still need an LDO here to convert the voltage. Okay, so definition and scope of this analog circuit. And uh, in this slide, I wish to share with you which kind of parameter we are concerning about, right? The first is the voltage. Yeah, why this is we concern the voltage because the input is just a very we call it a small signal, right? So why it is a small signal? It means that the voltage swing is quite small, right? It's a weak signal. So we have to amplify it before it can be it can be dealt by the ADC, right? So if the signal remain to be such weak and directly drive the ADC, what will happen? It cannot make the ADC to toggle between different states. The ADC will remain silent because the signal swing is too weak, right? So for this reason, we have to first amplify the voltage swing to sufficiently drive the ADC. Yeah, at least the ADC can toggle between different states and generate the digital code for the subsequent processing, right? So the second one is current. So people will, I think all of you have studied analog design before. So why we still concerned about current? Because we all know that actually we don't have input current input the MOS device, right? Because the MOS device is actually its input. Sometimes we refer to the gate. The gate is actually a oxide, right? It's a oxide. It forbid the current flowing into the gate. So why we talk about current? Yeah, because the first stage normally is not just it's not an amplifier. So the first stage is what? Okay, so the first stage is actually is here is okay. Okay, I forget, but it's okay. So the first stage is sensor, right? Here we still have a sensor. The first stage is a sensor. So why we talk about current? Because this sensor normally converts the this such a physical signal into current. So this normally how for example we convert the light or sound or even up signal into current first by the sensor, right? So actually, it's also the sensor is also naturally it is a converter circuit. It convert the signal from the nature to current first. So because the current is also very weak due to the loss of this sensor, we have to amplify something. Here we should amplify current. However, because the most device input normally is a gate, right? It's a it's an oxide, so the current cannot just go go through the oxide, right? So we have to have something, some device to convert such a weak current into voltage burst. So we we normally have a trans impedance amplifier, which is short for TIA, to convert the weak current into the voltage, right? So the first step, we have to convert this weak signal from the nature into the current, because this signal is not electronic signal. Yeah, this is a signal from the nature. So the first stage is actually a sensor, which is a converter to convert this signal into the current. The current is inherently an electronic signal, right? So the second stage, so which is what we have to focus during our lecture, start to amplify this convert voltage, right? To amplify and boost the swing of such a convert voltage. So we still have to concern about the current, and we have to concern how this current transform into voltage, and what is the loss of such a conversion. If if the conversion is loss instead of gain, then the voltage after converted is even smaller than than we anticipate. Yeah. So that's will decide how we can decide the gain of the amplifier when considering the loss of such conversion from current to voltage. Okay. So we still have to concern about the current for the signal chain here, not just concern about the voltage, right? Okay. So the next one is frequency. Yeah, the frequency refer to the frequency of the input signal. Yeah, during our undergraduate student, we normally say the input frequency, right? Okay. Uh, by saying this, we understand what is the ability of our amplifier and what is the highest frequency it can tackle for the input signal. Beyond such a frequency limit, it lost the ability to amplify it. Okay, so this is quite direct and simple. But somehow this is still not enough. Why? Because as we have mentioned before, uh, the analog chip will be integrated with all other building block. For example, the digital chip and the RF chip, right? And this chip will generate lots of harmonic and harm the analog chip. So maybe as a student we do not understand why this is harmful, but just think about it. Because we have to deal with a very small signal here, so if the signal with other frequency or the same frequency with the input come from other block saturate your amplifier here. No matter what is the input here and is large or is small, because your amplifier already saturate, your amplifier does not have the response to your amplifier does not respond to the input anymore. So we have to think about the frequency uh, other than the input signal. We have to concern this frequency from other building block of our chip. For example, the clock in the digital circuit, right? When we talk about AI chip or microprocessor, we normally have a clock frequency. The clock frequency is much different from the input frequency. Yeah, the clock frequency is, for example, for the Intel or AMD chip is maybe 5 gigahertz or even higher. But the input frequency vary from 100 megahertz to even high or even higher frequency. So it's a wide frequency range. But the clock frequency is quite fixed for microprocessor. So we have to consider the frequency as an important design matrix in our amplifier and do some filtering necessary to filter out the unwanted signal from this digital circuit. Yeah, by doing this, we can safely receive the signal from the nature because the other frequency has been suppressed by our specific design. If we do not have such a design, we cannot receive any signal here because your design already saturated. Okay. So another important factor like a phase, this charge phase is important when we discuss the phase lag or phase lead of your design. For example, when the input signal comes, it has a specific case. After your amplification, you can enlarge the voltage swing, but the phase also lag by a certain amount. If this phase lag is important, how you can compensate for this loss, this lag, or maybe it is not important for your transmission. Yeah, you have to decide if this important for your chip. Yeah. Another aspect is that the phase by observing the phase, you can get a direct observation of the phase margin of your amplifier. So you can decide if this transistor operate in the same region and what is the margin for this for your amplifier going to the unsafe region. Yeah, you must estimate correctly. Yeah, for the phase margin of this amplifier. Yeah. Also, there are many aspects here we can discuss during our lecture, but at least we must focus on voltage, right? Voltage is more important than maybe during the class because we focus on how to boosting the voltage by your amplifier. Right? Later we can have some short discussion on the current because the current conversion is also a challenge topic in analog circuit design. And we must also discuss the frequency, response of your circuit and how it can harm your device and how to avoid these harmonies. Yeah. We discuss the phase to determine the safe region and what's the margin of your amplification. Yeah. Okay. Yeah. Next. Signal trend in the real product. Okay. The signal source. Yeah, signal source, which is the input, right? Input from in most case it comes from an antenna. Yeah, the antenna will transmit the large signal into the power amplifier. The power amplifier will transmit the signal from through an antenna into the free space. However, because the propagation length, I mean the distance, propagation distance is too long for the transmission, the signal will witness a large loss during transmission, right? So this signal will enter our device but have a large loss to it. So that's why we have to learn to design the amplifier to amplify this big signal, right? The second important issue is the protection and biasing. So why this is important? From a direct observation, we have to keep the chip safe, right? Because this is a protection. So I think we have to study protection before in our second year study the analog circuit. So what we wish to protect is a diode, right? Because the diode follow the exponential relationship. So even I mean further increase the voltage until further increase the voltage will push the diode into a very to direct very large current. So we have to put a series resistor to protect it, right? So we have already studied this topic before. However, in the analog circuit, why this is very important? Yeah, that is because the chip has to interface with outer world by wire bonding, right? So after we fabricate the chip must be bound onto the board, right? We know the PCB, right? The chip must be bound onto the board and use the wire bonding to connect to the input output and also the DC pad. Okay, so why this process require protection? As we have learned from the semiconductor physics during the fabrication, during the fabrication of the wire bonding, the instantaneous charge will potentially cause a large current to the transistor gate, right? Because the transistor gate is made by oxide, which is very thin. I mean, so how thin is it? Probably just 3 or 5 nanometer. Is really very thin. Although it forbid the current flowing, but because it is too thin, it has we still have chance to breach to damage this gate oxide. Yeah. So if the gate is damaged, the transistor will fail anyway. Okay, so that's why we need a protection and biasing to make sure all the transistors connecting to the outer world must stay in safe region and cannot be uh, uh, damaged at any case. So normally we will have some ESD protection here, which is composed of some circuit, which is high voltage circuit and high voltage diode here. So why is high voltage why they must use high voltage here? It is because the instantaneous charge, because the time is too short, right? The time is too short. The charge amount is too large. If you create a instantaneous high voltage within a very short time to the device, to the gate device. Yeah. So our target here is to bypass such a damage current. Yeah. So how can we do it? So we put a pair of diode here. The diode must be able to sustain very high current, but remain in safe region, right? So once the charge come during the PCB the wire bonding fabrication. So the diode will simply direct bypass all the current to the ground and ensure the device after it is safe, because the device here can do not have a chance to observe any current flow, flowing into it, because the current will be bypassed by the diode here, right? Okay, so this is a protection and biasing, but this is actually not a focus of this class. Yeah, but we still have to mention it. Yeah. Later is the amplifier and filtering. Yeah, as we have mentioned. Yeah, because the amplifier is actually a nonlinear device. Yeah, and we still have to design some specific filter to filter out the unwanted harmonic of our design amplifier. The student will be question of this. Why just we design some highly linear amplifier to prevent such a harmonic generation? Yeah, it is possible, but as we have mentioned, highly linear amplifier normally sacrifice other parameters such as the gain. Yeah, because gain is very important for amplifier. So sacrificing gain sometimes is not very helpful for our system, although your system is highly linear. Yeah, so filter is somewhat useful here, and we spend a little bit time to describe how we can design a filter. Maybe it's by a passive filter or it's by a switch capacitor filter. Yeah, the passive filter, which made of RLC, resistor, capacitor, and inductor, is somewhat simple. That is somewhat simple. Uh, uh, then we can study the switch capacitor to uh, to perform the filtering functionality, and this is I think more difficult, but we still have some time to start it. Yeah. Okay, later is data conversion and ADC. Yeah, this is also a large topic. Yeah, I think we will not go into the detail of this in this class. And the last one is a digital processor. Yeah, it's actually a aspect of the digital design. Okay, so what is our task as an analog IC designer? We must understand our task. So the first task is to understand the specification, as we have mentioned before. So specification come from our tutor, for example, PhD tutor, or come from our customer, right? So for example, for a gain, 40 dB minus 1 dB. So this is a tough job, right? Because the gain should be flat, yeah, inside your bandwidth, and the 40 dB. So how can we achieve that? And then the bandwidth, for example, the 10 megahertz. If the gain is high, can we still preserve such a bandwidth for achieving such gain? And then the noise level, what is the noise level? Why is noise important? Because it will affect it will determine how large of your input signal to overcome the noise. If the input signal is even comparable to the noise, then the amplifier cannot distinguish between noise and your input signal, right? So you have to define the input refer noise. So what is the level? So for example, 10 nanovolt, yeah, per square hertz at 1 kilohertz. Yeah. So if your input signal is rather weaker than noise, or is too weak, so the as a signal to noise ratio will be damaged, right? So you have to think about the noise level and of your amplifier and try find a way to suppress it. And I think at the end you will understand maybe if, even though you can suppress noise, you must sacrifice something. Yeah, you must sacrifice. For example, the area. Why we have to sacrifice area? Because we suppress the flicker noise, right? We have to suppress flicker noise. The flicker noise is inversely proportional to the size of the transistor, and so we have to sacrifice the area for gaining sufficient low noise. However, for a large input device, the bandwidth is also reduced. So this is the trade-off between noise and bandwidth, right? Yeah, THD is referred to the linearity. Yeah, so it refer to the harmonic generation of your operating amplifier. So which means that your amplifier must generate sufficient low harmonic to and not to harm the subsequent device. Yeah, the power consumption, for example, 5 millivolt. Yeah, at 1.8 volt, is it reasonable? Yeah, we have to think about it. Can we further reduce it? So we have to do a power budget for our design. So, for example, how much percent from the current meter and how much percent for the input device? Because we need to separate noise, right? And how much power from the output stage? Yes, we have to do the power budget and think about what is the dominant power inside our core. And supply, this is actually a predefined, yeah, by the customer, which is normal nominal voltage is 1.8 volts. Sometimes it's 2.5 volts. Yeah. For advanced node transistor, it can be lower than 1 volt. Right. Okay, sometimes we have to consider their variation, like the supply variation and the temperature variation. We must do lots of, sufficient simulation to cover the variation of this supply and temperature, and make sure under extreme case, the circuits still fulfill about the requirement and do not enter the oscillation region, right? Okay, the next one is how can we choose appropriate proper architecture and topology. Yeah. During class we will study several topology configuration of the amplifier. We will make a comparison table between this topology, and this topology has their own advantage and disadvantages. So we have to summarize it. And during the interview, because time is too short, for a specific uh, question, you have answer clearly why you choose this configuration and why others cannot fulfill your spec. So this is actually referred to a design intuition, right? Okay, so we will do lots of homework to enhance our understanding to different architecture and topology. Yeah, so I think in the second year of analog study, we have studied the common source, which is quite common for amplification, and also the common gate, which is quite useful for the input stage matching, and also the common drain, yeah, which is quite useful for the output impedance matching as a buffer, right? So these topologies have their own merits, and when we can adopt these topologies, we must consider, right? And can we also combine them? Yeah. And for example, we combine all these three topology to simultaneously achieve input-output matching and also amplification, right? Okay, so after we integrate this stage, so what will be their eventual limitation? Okay, so what is their noise performance and linearity performance? So what is important is that we must tell clearly the interviewer. So which stage limits the noise gain and linearity? Yeah, for example, so if you wish to increase the gain, you should tune which stage and tune which transistor. You must understand the tune because there are more than for this case there are more than 10 transistors, I think. So you must understand which transistor to tune for each specification. Yeah. Okay, so we still learn the analysis as we have discussed before, and I think during the class I will do hand analysis for all of you. Yeah, instead showing slide like this. Yeah, I think in many class the 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 lecturer like to show slides, especially for some class. But I think it's not very direct. Yeah, I think a more direct way is to perform the hand analysis during the class by sequence, one by one. And I will explain in detail how this equation comes and why the equation important, right? Why we need this equation and the complexity of this equation is sufficient, or we need a more complex one, or we can make it compact and use a simpler one, right? I think in the interview you only have 10 minutes to explain to the expert. You do not expect a very complex one to show your thinking to the interview, the expert. So we choose equation and which is compact enough, but still give us a good insight into the circuit. And such a good insight normally can fit into the simulate result by your EDA tool. So this is what we wish to get, right? Not just a very complex equation that cannot be understand within 10 minutes. Yeah. Okay, so there are still a lot of slides here, but I think some of them are repeated. So I think we don't have too much time. Actually, the analog circuit is a very broad aspect covering lots of topic that cannot be fully covered in a few hours. Yeah, because they are as right now in modern analog circuit design, the analog circuit is not isolated. Maybe 10 years or even in the early age of uh, the course, the analog is somewhat isolated from other class. It just talk about amplification, right? But right now, analog is not isolated from other cores. Sometimes we have to incorporate the digital into the analog design. Yeah. So why is that? Because for example, we have maybe some of you have learned the filtering before, right? The filtering can be performed continuously by the RLC network, or or digitally by the switching capacitor circuit, right? So actually, in the switch capacitor circuit is because the filter must be clocked by by a certain frequency. It's very hard to uh, say it's a pure analog circuit. But it is not a digital circuit because there is no binary calculation inside the filter. So it's actually an analog and digital collaboration when we study the filter. So we cannot simply think analog is just amplification of continuous signal from the nature. We must incorporate the analog circuit with digital partner to perform some specific task like filtering or conversion, right? Analog to digital conversion or inverse. Sometimes when we design the clock generator, actually it's the clock generator combine analog circuit and also digital circuit, right? So for example, the voltage control oscillator is an RF circuit. Yeah, it's or more specifically, it can be analog circuit anyway. Yeah, and then we have a frequency divider, right? Frequency divider we have to then convert the high frequency into a low frequency signal. So this frequency conversion can be designed in both analog and digital fashion. Okay, so each of them has its own merits. Analog fashion is more direct, but it consumes high power. Digital circuit is more complex. Yeah, use more transistor, but it can be configurable. So it depends on the scenario. Your circuit is target to, right? So in the phase detector, it can be also designed in both fashion or combined together. So it's hard to distinguish is a pure analog or pure digital. Yeah, in the end, the filter can be analog filter or digital or combined filter, right? So it's okay. We study in the university that we focus on pure analog circuit and focus on the amplification. Yeah, because this is a good foundation for us. But in the industry, before you go into the interview, you must understand in a modern circuit design, this thing, analog and digital must be merged together to perform some specific functionality. Yeah. Okay. Okay. So why is analog IC design is difficult? Yeah, because we have to incorporate all this parameter matrix together before we can create a schematic. We can create a circuit, right? So normally we have to the one of the most important factor will be the gain, right? Will be the gain. And during the class, we spend lots of time to calculate the gain, right? And the bandwidth and also the noise. We also spend some, I think, several days to explain how the noise is transferred from the input to the output, and then revert and then normalize to the input, right? And we will understand why the noise must be evaluated at the input, not at the output, right? Uh, I think many students will be confused why we have to consider noise at the input, because the noise at the output would directly affect the performance at the next stage. So why would consider noise at the input? So we will during the class we will explain in detail and have some specific circuit to to help us to understand, right? The power consumption is also important, yeah, because the customer is very curious, is concerned too much about the power, right? In our current in the future trend, the power should be scaled properly with the technology node, right? Also the linearity, right? The THD and the IP3. IP3 is we will explain in detail later. Okay. And the area, yeah, stability, phase margin, yeah, gain margin, yeah, something like that. Okay, so we have to still think about device verification and PVT dependence, PVT process voltage and temperature, right? So device variation means that we have after we fabricate the amplifier or the analog circuit, so this circuit will be distributed across the full wafer, right? We we don't know the the location of the chip when delivered to the custom. If the chip located at the edge or the chip located at the center, so due to the process variation and also the manufacturing control, their characteristic may be different. So this difference may be captured by our EDA tool, but not very sure. So during our design, we have to consider this process variation before we simulating before we fabricating this chip. This is to make sure in the extreme case, for example, we prefer design chips with we we assume the tree located at the center, which have a very well-defined characteristic. But if the tree is located elsewhere, for this case, we still get the circuit. We still allow the circuit to operate normally and fulfill all the specification. So this is to consider the process variation, right? The next is the voltage variation. So how it comes? It comes from the LDO, right? Because we sometimes we use the battery, which has a very good stability of the output voltage. for example, to 5 or to 7 volts. But our LDO is not ideal. Yeah. Although the battery is ideal, the LDO here we design is somewhat not ideal. It change its characteristic vary with the temperature. Yeah. So it vary with the environment. So we must anticipate that with this variation, so the chip, our chip can still function normally under the variation of the voltage. Sometimes we specify 20% of the variation of the voltage. So when we conduct a simulation, we must incorporate such a voltage variation, which is 20% variation, uh, and evaluate. So what is the response of our circuit? So is it still functioning well, or it enter into some other region that may impede the circuit uh, functioning? So we must consider this well. Yeah. The last one is the temperature. This is a very common variation in during our usage. Right. So for example, for some specs spectral usage, so the temperature can vary from minus 40 degree to 125. So it's a large variation actually. So we must make sure within this variation, the tree must work function well. Yeah. So is it possible? Is it possible to do that? Actually, it's a difficult one. Yeah. To be frankly, this is a very difficult one. So that's why we normally have to design some supportive circuit, right? This supportive circuit is not to help our circuit to provide uh, higher gain or larger bandwidth, but it is useful when the temperature changes or vary, right? So this supported circuit will compensate for the gain loss or the bandwidth loss when the temperature varies. Yeah. So which means that we still have we need to have a temperature sensor to track the temperature variation in a real time and compensate for your amplifier. Yeah. Within this variation changes. Yeah. Okay, layout plastic and mismatch. Okay, so I think during the interview they will ask you some question about layout, especially how to do the matching. I think this is I think they must ask this question. Yeah, how to do the matching, how to do the isolation between block, and how and which trace must be shortened to minimize its parasitic, and which trace is important and must be isolated from the substrate or some the outer environment. Yeah, and you must explain explicitly so why this trace can damage the performance of your chip, and what was your solution to keep this isolation, and what is the way and and what is and what would be the practical way to do it? Yeah. Okay, so no single bit solution. Yeah, because the uh because because your design choice is highly subject to the specification. So it's hard to get a optimal configuration or design choice directly from just maybe for example from hand calculation or just simple uh, uh, simulation, right? So sometimes we have to in a group we have to discuss several approach, and this approach will incorporate different configuration that possible to solve the issue. And more importantly, when you considering the PVT dependence, some topology start to become malfunction and or just hit the limits of the specification. So in this case, we still have to do more interactive design and from between our hand calculation and the simulation to check under the extreme extreme scenario, your circuit is still robust enough to cover all the aspect, all the specification here. Okay, so it's hard to tell there is a single best solution for your design. Yeah. So from this training, we will understand the trade-off between the different parameter and how if we wish to reach one beyond the trade-off, what must be sacrificed and what must be done to protect your tree from the PVT variation. Yeah. Okay, so the learning outcome, yeah, I think we have discussed before. Yeah. So we learned the specification analysis and then build a circuit to meet this specification. And then we do an interactive design procedure between the hand calculation and the simulation. More importantly, we should have plan B, right? Not just plan A. We must have plan B when considering the PVT dependency. Yeah, we must specify in under the extreme case, plan A is not sufficiently robust, but plan B may be better. But so this, is it plan B is much better? No, not for this case because this is this is too bad, right? This is too bad. For example, from -40 to -40 to 125. But in some real case application, the temperature can fix to around 25 is possible by the packaging or the heating I mean by some design outside of the chip. So you don't have to think about such a wide range of variation of the chip. So sometimes your plan A is still better than plan B, subject to the real application. So this will help us understand. So each plan, their pros and cons, and their limits, and when I show use which plan, right? Okay, we will have a exercise. I think at the almost at the end of our class. So we will have some real specification. For example, here. So I will give some specification here. This specification have been verified. Yeah. Before you conduct the experiment. So later you will decide something, or you can, if you think design is too difficult, you can tune. I can give you a real circuit, a real amplifier. But I won't tell you the transistor size at the beginning. So I will give you the spec and you tune the transistor until you can meet all the specification here. Yeah, for example, here. Yeah, until you decide. And at the end, you submit a report and you will tell me why your design choice can meet this target. Yeah, you must have some simple, at least some direct equation to quantify this result and show your thinking step. So why you can get such a result. Yeah. And if you still have time, you can consider this PVT dependency, yeah, variation. Process variation is done by Monte Carlo simulation. Voltage variation is simple. You just tune the voltage to which supply your circuit. Temperature is also easy to tune. Yeah. Then you will observe your circuit and evaluate if it is robust enough to meet all the design target here. And if it cannot meet the target here, how you can uh change your circuit until it can be a robust circuit. Right? Just show your thinking. Yeah. Okay, so I think we will go into all the detail when we conduct the class. And for example, fundamental concept including the DC bias point, right? This is the IV relationship curve we have studied during our third year's study, right? So this is a very famous square law curve, right? So in here is a cutoff, and then enter the linear region. After that is enter the saturation region. Yeah. So during the class, we'll try to understand why this happened. So what is the underlying physics behind this ideal relationship? And more importantly, how can we bias? How can we achieve optimum fitting, optimal uh, operating point Q by a simple, maybe by a common source amplifier? How can we choose the optimal Q here? Yeah. Later, we will study the signal swing and Heron. So signal swing, so normally the circuit will receive a small signal, as we have mentioned. Uh, unfortunately, we cannot decide what is the input signal. So we must discuss if the small signal input become larger than anticipate. So what will happen for the transistor? If the transistor going back to the cutoff or linear region, or it can still remain in the saturation region. And if we enter the linear region, so will be our solution to push it back to the saturation region and make sure the circuit remain in the amplification stage, right? And then we started a biasing, by the biasing topology for different kinds of amplifier. So each biasing technique have its own characteristic. Yeah, some biasing technique have the advantage like the accuracy, right? To maintain very good accuracy, like within 1% accuracy. But it may have to still stack multiple transistor. Yeah. Some biasing technique have maybe have higher noise or lower noise, and we'll discuss in detail, and we will do some simulation calculation before our simulation. So the bias point is quite important for analog circuit. This is quite different from for the digital circuit, because digital circuit just deal with the binary signal, right? Just 0, 1, yeah, periodic signal. But for such analog circuit is quite important because it will determine the ability of each transistor. Yeah. Okay, so DSEP operating condition, foundation of good design. So we will during the first or second course, we will study this DSEP operating condition, right? Okay, later we will study the current and voltage bias. Just we have mentioned. So some bias generation circuit is quite resilient to the PVT variation, but generate higher noise and must stack multiple transistors. Some other kinds of voltage bias generation has may has higher uh sorry higher sorry other voltage bias generation may have good accuracy, but it might generate lower noise. So when we have a specific design choice, we must consider which topology we wish to use, yeah, to meet the specification, and then we run the simulation to verify our thinking, right? Okay, signal swing and Heron we have discussed before. Supply and temperature variation we also discussed. And normally they are in the simulation they are we assume their variation is within 20%. And sometimes in the real world we have a lot of approach to keep them within the 20% assumption. Yeah, it's very possible, but to evaluate how robustness of your chip, we must run some variation simulation. Yeah. Okay, then we will study the single stage amplifier. We will this is I think this is the first week study. Later after we study the we review the semiconductor physics. Yeah, so we'll study the gain and the linearity, and what's the approach to increase gain or improve its bandwidth by sacrificing what parameter to achieve the our desired gain, and is it possible to create a feedback here to stabilize the amplifier? So what's the usage of the feedback, and how can we calculate the characteristic of such a single stage amplifier if we have a feedback here? Okay. So later we'll study the current mirror. We'll study the accuracy of the and also the mismatch of the current mirror when the current is mirrored from one golden reference to another branch. We will study what is the issue when we perform the current mirroring, and how accurate the current, and what is the noise performance of such a noise during such a mirroring. Yeah, we will study. Yeah, if the if so what kind of topology is preferred when we have a specific amplifier? Yeah. So later we will study the current source concept. In the different show pair, so different the current source is just at- so define the operating region of the one transistor. So we will study under the consumption of small signal or large signal. So what is the impact of such current source? So it is so how this current source can affect the gain, or it does not affect the gain of the differential topology. And we will also study under the large signal, what is the role of this current source. Yeah. So we will study the input-output characteristic for differential pair when incorporating the current source under the consumption of both small signal and large signal. Yeah. Okay, then we will study active low. So why this is important? Why it cannot be replaced by a simple resistor? So we will study this. We will study this why we need an active low when we designing a amplifier, right? Okay. So I think we still have some slide here, but I think we do not have too much time to go through all for it. But I believe during the class, I think in October, starting at October, we will study all of these fundamental issue. In during our class, we can keep communication and all the time. If you have, I think some student worry about the future, right? The after starting this course, I think what I can provide is that I actually have some experience of the interview, so I understand what experts prefer. Yeah, so actually our target is to maximize the chance within just 10 or 15 minutes of discussion. So the design intuition is quite important. So this actually requires us to make comparison before different circuit topology. We must fully understand. So what is their limit? So what is their respective proof and cons? or uh, so when we have so some expert will ask you a real case study, a real case study. So you must show explicitly to the reviewer. So why so which topology is more suitable to meet the spec of what they are saying, and why other topology cannot meet the requirement. And then when you considering the PVT effect, how you can combine these different topology into a whole to overcome this, overcome, possibly to overcome the PVT. Sometimes the question will not be very difficult, but it's because they are the real case design real case design. It cannot be a single transistor, right? Something it will like here the feedback here. The feedback here is much more difficult than a single stage open loop amplifier. Yeah, because it is related to the design of the single stage, sorry, the open loop amplifier here, and also the feedback here. So how you can construct such a feedback? Because we have a four type of feedback. So which type of feedback you use and which kind of amplifier you prefer, right? So I think during the class I can how to say, I can mimic the expert. So I will show you what expert will ask you during the interview and how you can gain quickly insights from what you have learned during the class. Yeah. So I think this is what except for the lecturing except for the lecturing, this is what I can provide for the student.